Let's talk about the water on the Earth's surface. The water, in addition to the soil, is one of our very precious resources, something we need to survive as human beings. 97.5% of all water is in oceans, and it's salt water. Of the remaining 2.5%, that's all fresh water. 68% of that is locked up in glaciers and ice in areas that are difficult to get that water. 21% is then underground, 10% is in the atmosphere, and only 1% in rivers, lakes, and inland seas and soil moisture. Water in the atmosphere holds, transports, and releases solar energy, distributing heat around the world, and so water has a very important role in our lives. Continuous movement of water between the Earth's four spheres, the atmosphere, the hydrosphere, the lithosphere, and the biosphere, is called the water cycle. The energy to drive the water cycle comes from the sun, and there are four major mechanisms of movement, and I'm sure you've kind of studied these before, but I'll just remind you of them as we go through the next set of slides here. Evaporation is the first one. The sun's energy enters the water molecules and creates a situation where the water molecules begin to move faster. They turn into a gas to form water vapor, and thus evaporation forms. Water evaporates from bodies of water, from falling precipitation. It evaporates from soil. If water evaporates from the surface of plants, they call that transpiration. Condensation occurs when the water vapor begins to slow down, and the water molecules slow down, and they slow down so much that they form up liquid water droplets again. Usually these liquid water droplets cling on to little dust particles or microscopic organisms or things floating around in the air, and they become essentially little cloud droplets and fog droplets. Precipitation occurs when the condensation builds up so much, typically in a large cloud, that the water droplets will come together to form up a large water droplet that can fall down from the sky to form precipitation. Precipitation forms include rain, snow, sleet, and hail. And then runoff occurs, of course, when the precipitation reaches the land surface. Liquid water runs over the land, or the lithosphere, and back into the bodies of water, the hydrosphere. And so, thus, the cycle of water is complete. Of course, when the ground can't absorb precipitation, the water runs off even greater, in greater amounts. Steep slopes, little or no vegetation, fast, heavy rains, saturated or frozen ground, all produce more runoff. And then, of course, some of the precipitation does soak into the ground and make its way through the ground in the system of groundwater. Eventually, groundwater does make it back into the hydrosphere, either in rivers or lakes or even the ocean. And so this is a visualization of all those processes we just talked about, where evaporation on the picture on the right side there and transpiration creates water vapor through the sun's driving power. That evaporated water then condenses to form rain or snow or any other types of precipitation, which hit the ground, either freeze as glacial material, run off in the streams and rivers, and or soaks into the ground as groundwater. Another interesting little addition of water into our atmosphere comes from volcanic eruptions. Believe it or not, about over 50% of all water or of all gases in volcanic eruptions is water vapor, and so additional amounts of water are added to the atmosphere through volcanic eruptions. Let's take a look at the specifics of groundwater, because that's actually the type of water that most municipalities and people use, including areas around Malta. Groundwater is the water that seeps down through the soil. It occupies the air-filled openings or pore spaces between rock particles. You see that pictured in the upper right there. And 90% of the Earth's liquid fresh water is stored in groundwater, so it's a very important resource for us. An aquifer is what they refer to as a body of rock that holds and moves large amounts of water. Example aquifers would be something like a sandstone that has large pore spaces where water can move through very easily, or limestone, rock that has lots of fractures, or conduits where the water can kind of flow around underneath the ground. The amount of water a rock can hold is referred to as the porosity of a rock. The percentage of open spaces between the rock grains is another way of saying it. The more porous the rock, the more groundwater it can hold and the better kind of aquifer it will be. You can see pictured here, greater porosity occurs when rocks have kind of more like the same grain size. If you got rocks with or sediments that have grains that have varying sizes, even smaller grains, then those small grains get in between the pore spaces of the larger grains and take up space, producing a situation where you have very much a lower porosity. Porosity then is influenced by the sorting or sizes of the rock grains. Well-sorted grains usually have grains all about the same size. That means you're going to generally have a better porosity. And poorly sorted grains, or grains of all different sizes, are going to generally produce a poor porosity or low porosity. And that's pictured here in the bottom picture. Permeability is how freely water can move through a rock. It's the amount of connectedness of the pore spaces. Generally, coarse-grained rocks have better permeability. Impermeable rocks are those where the pore spaces are not connected and have very fine grains. Generally, the larger and more similar the grains, the better the permeability. And it's also of note that a rock can be high in porosity but low in permeability. You can see pictured in the bottom there, you have, on the bottom left particularly, you have a fractured shale that has a decent amount of pore spaces to hold water, but it's very impermeable because those pore spaces are not connected. Whereas you see the uncemented sandstone there has lots of space in between the grains to allow for water to flow. Now the zones underground where water exists are labeled specifically as the zones of saturation. The zone of saturation is where the water kind of drains down to and then kind of starts to fill up underground. The zone of saturation is usually close to the surface in very damp or wet areas, and the zone of saturation, the surface of it is usually a little bit lower in drier areas. The top of the zone of saturation, that's called the water table. So if you are a person that would like to use the groundwater, you would have to dig a well all the way past the water table in order to get water for that well. The area above the water table in the zone of saturation is known as the zone of aeration. This is where the grains of the rocks are generally filled up with just mostly air. And when it rains or when water starts to soak through the ground, it might have a little water in it, but then mostly air for the rest of the time. There is a little zone near the surface called the soil water zone, and this is where a film of water usually remains around the topsoil grains because the life and organics at the surface provide for that. The water table generally follows the shape of the land. It rises in wet conditions and lowers in drought conditions. And it is the groundwater is affected by the permeability of the rock. The more permeable the rock, the greater the flow of groundwater. And of course, groundwater flows from higher to lower pressure. So if you have a river in the area, groundwater will actually flow upward toward the river because that's the low pressure area, the area where water is being taken from the system. And so groundwater gradient usually flows in that area, in that direction. As I said before, in an ordinary well, you drill down past the water table so you can obtain water from that well. It's in what we call an unconfined aquifer, an area of rock that's just recharged from the rainwater from the surface. The area below the water table then is an area where we can get water. Now there is, you can see in the picture here, there's also a so-called confining layer underground oftentimes. This is a rock layer in which water cannot pass through very easily, an impermeable layer, which means that the water that's below that is confined from the surface. It has to be recharged from a distant area, and this confined area is known as a confined. Larger towns like DeKalb and the surrounding area have to drill deeper into these confined aquifers for a large supply of groundwater and a more reliable supply of groundwater. As you can see pictured in the upper right there, the recharge area for a confined aquifer in the picture is way off to the left. It rains in that area, the water soaks into the ground, and then it hits the water table and begins to flow downward into the confined aquifer. Then the area then further down the way, when they drill down for a well, they want to go right into that confined aquifer because that's a real clean and ample supply of water. The ground actually naturally filters the water in there to produce a pretty clean source of water for areas. An example of a large aquifer is the Ogallala aquifer, which supplies water for pretty much most of the Great Plains areas. You can see that pictured in the picture below here on the bottom right. Let's talk about some of the features that are formed from groundwater, particularly karst topography. Karst topography is an area that is underlain by much limestone, and that limestone is worked over by the groundwater. Groundwater goes into the limestone, gets into the cracks, dissolves away a lot of the limestone. It leaves behind little caves and caverns and little passages for the water to move through. If you get a lot of time involved, the chemical weathering that's produced by this groundwater really produces some large caves, and sometimes the underground caves collapse. The roofs of those collapse to form sinkholes. Disappearing streams, natural bridges, springs and caverns and caves, stalactites, stalagmites, these are all features of karst topography, and you can see some of them in the picture here. The acidic rainwater goes in. It soaks into the ground through the cracks in the limestone. The limestone is further chemically weathered away to produce larger cracks, which eventually end up forming the caves and caverns and all that kind of good stuff. Of course, limestone, when it's worked over by water, can produce some pretty amazing land features, and so you can see those pictured here. I believe the picture on the upper right is the so-called stone forest in China. The lower right there is a large sinkhole, which I believe is in Guatemala City in Guatemala. And on the left here, you can see a nice beautiful cave in the upper left, and the lower left some springs of water coming out the sides of a hillside in a limestone area due to the fractures that carry the water.